Hello, I'm Matt Roush with Lawrence Technological University. I'm here today with George Moschelli, who's a professor of physics in Lawrence Tech's College of Arts and Sciences. We had a bit of news today that some are calling a breakthrough. Scientists at Lawrence Livermore Labs in California achieved a positive net energy result out of a fusion reaction. They said they fed 2.05 megajoules of energy into a chamber and got 3.15 megajoules of energy out. A joule is a measurement of energy, and Science magazine said that 3 megajoules is roughly equivalent to 3 sticks of dynamite, so a pretty substantial amount of energy. So we're going to talk about this a little bit and what this breakthrough possibly means. First of all, Dr. Moschelli, explain to us in simple terms what nuclear fusion is.
All right, well, nuclear fusion is, as you say, it's got the word nuclear in it, so it's a nuclear reaction. And it's just taking the bare nuclei of atoms and pressing them together hard enough until they fuse, that's where the word fusion comes from, until they fuse into a heavier nucleus. And generally, depending on which nuclei you're using, the mass of the two nuclei you're pressing together is a little bit more than the mass of the nuclei that you get as a result. So that difference in mass becomes the energy that's released.
Okay.
So in this experiment, they're using hydrogen. That's the simplest nucleus. It's just one proton is hydrogen, and they're pressing different kinds of hydrogen together to make helium, and that reaction is the one that releases the energy.
So what exactly did the scientists at Lawrence Livermore achieve today? Or what did they, well, that was announced today. They achieved it a couple of weeks ago.
Well, so really what their achievement was, I mean, like you said, is that there was a net energy gain. So it's the first time ever that a fusion reaction has been created that creates more energy than it took to produce the fusion. At least in terms of a controlled way. Like, we've created fusion in other ways, like with bombs, right?
Yeah.
Like so a fusion bomb is actually a fission bomb where the explosion from the fission bomb is used to provide the force to compress the nuclei, and then that fusion then makes another reaction that is the fusion bomb. So what they achieved this time was you can do it in a small contained way. So they used lasers to heat up the hydrogen fuel, and they had the fuel contained in a very special way, which in itself, like the containment, is a very big advancement. So how they used the lasers to heat it up was a very big technological advancement, and they did a lot of work to control how the lasers interact, control how the energy from the lasers is absorbed by the fuel, and then the thing that contains the fuel, how that reacts to gaining the energy, so that it does this compression action where actually the fuel pellet that's there explodes, and that explosion sends a pressure wave inside to the fuel, compresses the fuel, and then the fusion happens. So all of those took years and years of technological advancements of how to set it up right, how to make a laser that's powerful enough to do it, how to make the container for the fuel that works, that doesn't break in the wrong way, so that the shock wave can make enough pressure to do the fusion. All those things were really big technological advancements. So that's what they really achieved, is how do you make the device so that you can have a fusion explosion, a tiny little explosion that's tiny and not a nuclear bomb.
Right. So why is this important? I mean, what is the practical, I guess, implications of this?
So fusion is like the great hope for energy independence. So first of all, the fuels are very abundant. It's not like there's rare fuels that you have to mine from the ground. The fuel is hydrogen, and it turns into helium. So not only is the fuel very abundant, the waste is helium, and that's not something you have to worry about storing. It's not what you would call, what we worry about with nuclear waste. It doesn't produce carbon gases that ruin the environment or the atmosphere. So that source of clean, sustainable energy would give us energy independence. And also, this technology keeps us at the forefront of nuclear technology. Like you'll hear, if you look into it, you'll hear a lot of talk about national security, which is now that we can create controlled reactions to test technology that controls fusion in a way where you don't have to have a giant explosion anymore. So not only is it energy independence, it's also a national security issue for the development of technology.
So does this achievement bring us closer to having fusion power as an actual energy source?
Yes, it does. I mean, it's not going to make it like tomorrow. I think even just building a power plant like that, if you had everything all set, would take 10 years. So this is just the first step. Like they've created a reaction that they can ignite on command. And they still have to do further tests. Like, the real question now is, can they do this test again and get the same result? They've had the first breakthrough. Can you do it again?
That's what science is all about.
Yeah.
Right? Yeah.
And then there's all the technological problems of, can you do it again very often, right? They did it once. Now you got to do it many, many times a second if you want to have enough power to do a power plant. And then there's all the engineering challenges that will come with, this thing is producing heat. How do you use that heat to actually create electricity? That's a whole different puzzle that they're not even thinking about. They're like, can we just get this fusion to happen? So there's a lot of big steps coming, but it's still very exciting.
Okay. So how far off do you think it is before this can be an actual power source?
Yeah, so like I said, even if you had all the fusion stuff understood, it would probably take 10 years to build a power plant, another 10 years to plan one. So that's already 20 years. And now, the way science works is it doesn't go like really slow progress. It's like no progress until we finally understand something, and then there can be a big jump, right? A big leap in understanding. And that's what everybody's hoping that this is. That there's this big leap in understanding, and we'll get the fusion part figured out, and now we can go on and start worrying about how do you design the power plant. So just the designing and building the power plants, 20 years. I'd say add another 10 years for getting the fusion stuff to be like, you can do it on command and a lot. So maybe 30 years would be my guess, 40.
Okay. All right. Well, welcome to your power source from the year 2050 or 2060, I guess. So last question, tell us a little bit about your work here at Lawrence Tech. I know you've gotten some federal grants for your research. Tell us just a bit about your research.
So my work is actually, even this fusion reaction has gotten me thinking about my work. In my work, we actually collide nuclei together to try and make a tiny explosion and see new stuff come out. And the way that they do that is they have big accelerators that take the nuclei and they slam them together as hard as you can. This technology actually makes a little smaller containment and pushes them together with lasers instead of big accelerating rings. So what I do is I do the theory for these nuclear collisions to try and understand how the strong forces inside the nucleus produce new things. This could be a new way for experiments to be made to produce new types of nuclear reactions that I could study. Yeah. But that might also be a ways off.
Okay, thanks very much, George Moschelli, professor of physics here at Lawrence Technological University.